lines given the equations of the lines. You'll need to know this before you do problems 13 and 14 in the book. You can also read it in the book on page 3, bottom of page 376, up through the top of page 377. Right? So I'm going to start by drawing two lines. The red line, we're going to say that the slope of this red line is m1, and that its angle of inclination right here is alpha, and the blue line is going to have a slope of m2, and its angle of inclination, again the angle of inclination is the angle formed from the horizontal in the counterclockwise direction, so it's going to be beta. And again, just a reminder that the angle of inclination and the slope are related, because if you take we'll do it over here. If we take the angle of inclination and use that to find the slope, again the slope, if we were to start here, say at this point and come up to this point, the slope is rise over run, so this would be the rise, which is going to be sine beta. This would be the run, which would be cosine beta. And then slope is rise over run, so the slope of this, our m1, would be the rise over the run, the rise being sine beta, sine with an n, and the run being cosine beta, which is the tangent of beta. Okay, so back to our problem. So we've got the red line, it's got a slope of m1. We've got the blue line, it's got a slope of m2, and we are interested in knowing what this angle is here. And we're going to call this angle theta. So we've got beta, alpha, and theta, and so we've got this angle, and this angle, and they're all tucked inside of this triangle right here. And the relationship between these three is that, if you remember from geometry in the 9th grade, this is called the exterior angle. These are called the two remote interior angles. This angle here, I'll just call it for now, I'll call it x. These three angles, 1, 2, 3, equal 180 degrees together. These two angles equal 180 degrees together. Right? So if these three equal 180 and these two equal 180, then the two remote interior angles equal the exterior angle. So we can write that, right, that alpha is equal to beta plus theta. And then if we solve that for theta, what we have is theta is equal to alpha minus beta. So now if we want to find the measure of this angle, if we're looking for angle theta, we can use what we used, the tangent identity that we learned in class, and it's going to work this way. We're going to start by saying, I wonder what the tangent of theta is. And there's no particular reason why you should notice that, I should be looking for the tangent of theta. Really what I'm looking for is theta. But when we look for the tangent of theta, it turns out that that gives us an interesting way to find what theta is. Now, theta is alpha minus beta, so that would mean that the tangent of theta would be the same thing as the tangent of alpha minus beta. Right? And again, not quite clear why we're looking for this, but just follow along. Now, in class, we had the tangent difference identity, and what we learned is that, like the sine and the cosine sum and difference identities, there's a pattern to this, and for the difference, it is the tangent of theta, the tangent of alpha minus the tangent of beta, all divided by 1 plus tangent alpha times tangent beta. Again, not quite sure why we're going this direction, but follow along. Stay put. Now, the tangent of alpha. The tangent of alpha is, well, alpha is this angle down here. Alpha is the angle of inclination. We know that the angle of inclination and the slope are related. The tangent of alpha, is m1. So if I have m1, if I have the slope of this red line, I can plop it into here. Right? So this is going to be equal to, so wherever I see a tangent of alpha, I'm going to put m1. And over here, this is plus m1. And wherever I see a tangent of beta, right, the tangent of beta here is the same thing as m. Ooh, hold on. This is a 2. Let's make this clearer. m2, and this is a m2. Right, so all of this little bit that I did in purple with sine beta, cosine beta, really what I was referring to is m2. So up here, tangent of beta is m2, and then tangent of alpha, which was m1, gets multiplied by the tangent of beta, which is m2. Which then means that if I want to find the what alpha is, I can just take the inverse tangent of all of this. And these numbers, all of this expression here, m1 minus m2, all divided by 1 plus m1 times m2, that I can get from the slope of my red line and the slope of my blue line. All right, so let's look at an example. So this is the example out of the book, example 2 on page 377, and we're looking at these two lines. Y is equal to 3x plus 1, y is equal to 5 minus 2x. So the two lines, if we graph of the two of them, that was pretty quick, huh? They might look something like this. And what we're interested in is we're looking for the angle between them. Now, there are two angles between them. There's this angle here, call this angle theta 1, and there's this angle here, we can call that angle theta 2. And most of the problems that you're going to be doing, they're going to just simply ask for what are the two angles between them, right? So, and again, reminding you of your geometry, if this is theta 1, this one also is theta 1, and if this is theta 2, this is the exact same thing here. So at this intersection, there really are two angle measures we're interested in. If we're looking for the both of them, well, if I find one, I subtract it from 180 to get the other. And if you're not sure which one you have, you can always take a sketch, quick sketch, to kind of get a sense of which of the two is the bigger angles. So if we're looking for what the angle is between them, we're going to use the formula pattern that we just noticed, or we just walked you through. Right? So we're going to looking for theta. So we know that the tangent of theta, and here we're going to look for theta 1, is going to be equal to, we're going to do, since we're doing theta 1, this is our alpha here, this is our beta here, right? So angle of inclination here, right? That's the alpha, what we referred to on the previous page as the alpha, and then this one here is our beta, right? So we're doing alpha minus beta, which is going to give us our theta up here. So this is then going to be equal to the, actually we'll write out the formula here and then we'll fill it in. So this is m1 plus, oops, not plus, m1 minus m2 all over 1 plus m1 m2, and then we start plugging stuff in, right? So we're going to figure out what m1 is, we're going to figure out what m2 is, and we're going to plug that in here. Right? So first off, m1, that's going to be 3. So 3 here, 3 here. m2, that's going to be negative 2. Negative 2 here, negative 2 here, and then we simplify. And this simplifies to be negative 1. So this theta 1, right, so the tangent of theta 1 is going to be equal to negative 1, which then means that theta 1 is going to be equal to 135 degrees. So this angle here is 135 degrees, which then means that this angle here, theta 2, must be 180 minus 135 degrees, which is 45 degrees. And then notice if you instead had done this the other way around and you'd if you had switched your m1s and m2s, what you would have been finding is you would have been finding tangent of theta 2, and that would then end up being negative 2 minus 3 all over 1 plus negative 2 times 3, which would then give you positive 1, and the inverse tangent of positive 1 is going to be 45 degrees. So if you do it the one way, the 3 minus the negative 2, that'll give you the one angle. If you do it the other way, it'll give you the other angle. And if they're looking for two angles, it doesn't matter which way you do it, because once you get the first, you subtract it from 180 to get the second. And that's what you need to know about the angles between two lines.